Hello everyone, and welcome to another video in my design guide series, a series where I break down some of the fundamental application circuits that are used in modern electronics. Today, we're going to be going over a circuit known as the H-bridge. This is a circuit that is commonly used to drive DC motors, but it also has a few other applications as well. So we're going to be running some simulations, doing some circuit analysis, and then discussing the theory of operations of the H-bridge. But before we go any further, please go ahead and drop a like on the video for me. It helps my channel a ton, and subscribe so you can stay up to date with any future videos. And with that out of the way, let's just jump right into it. So H-bridge basics. The basic diagram for an H-bridge is the one that is depicted right here, where you have these 4 switches in this configuration with some sort of load or DC motor in the center. And the reason it's called an H-bridge is because it looks like the capital letter H. The basic operating premise is that by opening and closing these 4 switches in a particular configuration, you can control the direction of current flowing through the load or through our motor. So as you can see, we have 2 of the switches are connected to our VCC, or in this case, it is 12 volts on the what we call the high side, and then 2 of the switches are connected to ground, or known as the low side of an H-bridge. So let's start off by closing switches Q1 and Q4 and seeing what happens. So note that when I click run, we can see that current, and let's slow this down just a little bit so we can. So note that when I click run, we see that by closing Q1 and Q4, we have created a pathway to ground through our motor that causes current to flow from left to right through our motor. Now, it's very critical during this time that switches Q3 and Q2 remain open, because let's say I were to do something like this, we would completely short circuit our 12 volt supply to ground, and number one, that would perhaps cause damage to our 12 volt supply, but 2, it would completely bypass our motor, and so it would completely stop the motor, right? So it's equally as critical that Q3 and Q2 remain open as it is that Q1 and Q4 remain closed. Now let's try opening switches Q1 and Q4 and closing switches Q2 and Q3 and seeing what happens. So as you can see, by closing switches Q2 and Q3, we have created a pathway to ground that allows the current to flow through the motor, but in this case, it's flowing from right to left. So it's flowing in the opposite direction as it was in the previous configuration. Again, it's equally important that switches Q1 and Q4 remain open in this time, because doing something like closing Q4 would short circuit our 12 volt supply again and completely bypass the motor. And this is the basic theory of operations for an H-bridge circuit. By opening and closing these 4 switches in a particular configuration, we can control the direction of the current flowing through the motor. So now that we understand the basic theory of operations for an H-bridge, let's take a look at an example that more closely resembles something you might find in the real world. So here we have again another H-bridge circuit that uses a set of bipolar junction transistors, or BJTs for short, in order to control the direction of current flowing through the motor. So we basically replaced those generic switches we saw in the first example with some transistors. So the very first thing I want to draw your attention to is that this circuit actually uses 2 PNP transistors, which would be Q1 and Q3, as well as 2 NPN transistors, which would be Q2 and Q4. Now, if you do some searching around on the internet, you will find H-bridge circuit designs that actually use 4 NPN transistors as opposed to 2 NPN and 2 PNPs, and that's a totally viable option. You just need to be aware of the differences in the designs between using a 4 NPN configuration versus a 2 NPN, 2 PNP configuration. This example, like I mentioned, it covers the 2 PNP, 2 NPN configuration, so that's kind of what we're going to be going over today. The second detail I want to draw your attention to is that this circuit actually uses 6 transistors in total to operate, and not 4 like you may have anticipated. So let's take a look at the Q1, Q6 little sub-circuit right here in the top left, and just to get a closer look at what's going on and why we're using 2 transistors versus the one that you might have expected. So real quick, I just want to go over here to explain. If you're unfamiliar with how a PNP transistor works as opposed to an NPN, they're very similar. The only main difference is that it's the current flowing out of the base pin, which controls the current through the collector, as opposed on an NPN, it's the current flowing into the base pin that controls the current through the collector. So I have here just a little example of a PNP transistor hooked up to show you kind of how it works. The way electrical engineers usually use PNP transistors is by placing a current limiting resistor between the base pin, and then on this other side we would have a ground connection. So that whenever I run this simulation, right here we see that we have current flowing out of the base pin, which allows the PNP transistor to conduct. So if you're extremely observant, you might have noticed then that what this means is that in order to get a PNP transistor to stop conducting or enter its cutoff region, you would have to bring the voltage of this point, this node right here, would have to be pulled up to VCC, or in this case, 12 volts. And by looking at the rest of the circuit here, maybe you already see where I'm going with this. So let's say we're trying to control a PNP transistor with the GPIO pin of a microcontroller, which typically the maximum output voltage of a microcontroller is about 3.3 volts. So with a microcontroller, your options are 3.3 volts or 0 volts, right? Which is why I have this switch here toggling between 3.3 and ground. And so if you notice, whenever I switch to 3.3 volts, yeah, the current slows down a little bit because there's less current flowing out of the base pin, but it's not zero, which means no matter whether I drive it to 0 volts or 3.3, I can't actually prevent this transistor from entering the cutoff region, right? So if we go over here real quick, that's going to be the equivalent of, say we had the configuration where we had Q3 and Q2 switches closed. Well, you would never be able to fully actually open Q1. So you'd have that scenario that I just laid out earlier where you'd be short circuiting this 12 volt to ground. This effectively would be useless. You wouldn't be able to actually do anything with just a PNP transistor, a current limiting resistor, and a GPIO pin of a microcontroller. So now you're probably wondering, okay, so what if we want to control a PNP transistor with a microcontroller GPIO pin? What are we supposed to do? And that's where the second NPN transistor actually comes in. So what we're going to do is we're going to use the NPN transistor, or in this example Q6, to act as a switch in order to toggle between 12 volts and ground. So let's take a look at our two sort of like operating configurations here, right? So we'll say configuration 1 is where Q1 is conducting, creating a pathway to ground, i.e. it's allowing current to flow through it to ground, which means that if we look over here, if we look from our 12 volt source, we see that current is flowing into our emitter pin and out of our base pin, right? So it's conducting, which means, so let's take a look at the two operating modes for Q6. As you can see, whenever I apply 3.3 volts to the base pin of Q6, we have current now flowing into its base pin and then out of its emitter pin, which allows it to conduct, thus creating a pathway to ground for the PNP transistor's current to flow into its emitter pin and out of its base pin, right? So we're basically connecting this little node right here to ground whenever this NPN transistor is conducting. Whenever Q6 is conducting, we have a connection to ground that allows current to flow out of the base pin of the PNP. Then whenever I apply 0 volts to this pin, Q6 is no longer conducting to ground. It's cut off, meaning this is like an open switch right here. So this node right here is essentially pulled up to 12 volts through this pull-up resistor, right? So what we're effectively doing is we're toggling this little node right here is either going to be 12 volts or 0 volts, which is exactly what we need it to be in order to use the PNP transistor. And just to kind of bring it full circle, right? The reason I showed this example with a 3.3 volt source is because that is what the typical GPIO pin for a microcontroller, that's what its typical output voltage would be, right? So we are now, what we've done by using this configuration setup is we are now able to control a PNP transistor with a 3.3 volt GPIO pin of a microcontroller. So that's what this little switch represents, is it's either a high or a low signal from a microcontroller. Okay, so I hope that part makes sense to you. Real quick, I just want to zoom out and kind of show you that it should operate exactly the same as the previous example, where just pay attention to Q1 and Q4. So whenever I apply this one, see we have current flowing from left to right, just like in the example. And let me slow this down for you. Just like in the example, in the first example where we showed the two switches are closed, right? So when this is high right here and this one is high down here, we have both of these switches are closed. And then when I want to do 0 volts, For both of these, everything stops conducting. We have no current flow at all. And then when I pull this one high and this one high, we now have current flowing in the opposite direction, just like what is causing the same thing. It's causing Q3 to be closed and Q2 to be closed. And now current is flowing from right to left. So that's the exact same result that we got in the initial example where we were just using generic switches. And this time we're using some real world actual components to do this. So that pretty much covers everything I wanted to talk about in this video. If you have any questions, feel free to drop them in the comment section below. I respond to every single comment I get. So don't hesitate to, ask me any of those questions you might have. And thank you so much. If you made it to the end of this video, hopefully I will see you in the next one.